right now, if you're staring at this thing for the first time, it looks like a bunch of Greek, because most of this we haven't seen yet. So very quickly, we've seen the basics. We've seen products and quotients on the tattoo. We've seen the first derivative and the second derivative, and we've been sort of exposed to the fourth derivative. So today we're going to pick up that third derivative and finish up the logs and exponents stuff. You guys ready? Good times. So ready. I have a couple of really nasty problems I want to throw at you guys. So just as a quick reminder, y equals 7x squared minus 10 divided by 15x plus 3x cubed would be a quotient if you were to take the derivative, right? But we have different rules for logarithms. So if I make this y equals the natural log of this stuff, there are shortcuts that can help us make it manageable. Yes, you can do this process here. You can take the derivative of the inside, which is a quotient, so you'd have to do u prime v minus uv prime over v squared, all over this thing as your denominator. You could do that, but that's a mucking fest, right? Nobody wants to do that to themselves. So we look for shortcuts. Natural logs have natural shortcuts. Can anybody find a natural log of something over something on their tattoo? Under the logs and exponents stuff? Yeah, you can. Emily, move your paper.
It's right here.
No, you're covering what you need. Trust me.
It's the whole section.
It's that whole section. Trust me, it's down there.
I found it.
You found it. What is it?
Log A of x equals log x of y.
Does that look like this? No.
Where?
We're looking for natural log of a function over a function.
Log n over n.
Yes, log of m, natural log of m over n. And these are not derivatives, guys. These are just ways to pick this apart so we can make it chewable. Nobody's gonna eat a whole steak at once. You're gonna cut off a bit and chew it one piece at a time. These are like steaks, okay? They're big, they're meaty, they got lots of parts. Chop one piece off and eat it at a time so you don't choke. So what does this split up into? Natural log of m minus natural log of n. So we're just gonna split this sucker up. Here we go. So y equals the natural log of 7x squared minus 10 minus the natural log of 15x plus 3x cubed. This is the natural log version of making it pretty. We are just getting it into a form that allows us to easily take the derivative. You guys ready? What's the derivative? Don't overthink it. What's the derivative of this? Yep. And then what goes on the bottom?
7x squared minus 10.
Good. Minus. Now we do the next one. What's the derivative of that?
15 plus 9 x squared over 15x plus 3x cubed.
Oh, look how pretty that is.
So you
Is
don't.
that prettier than that mess I told you about?
Yeah.
U prime v minus uv prime over v squared all over that thing?
So you leave out the ln's
Yeah.
when you do that.
It's not part of the derivative. Look, it disappears.
Yeah.
And the reason it disappears, guys, who missed last time, naughty, is the slope of the natural log is tied to the x value. So whatever your x is, the slope is gonna be 1 over x. So if we take the natural log of x, its derivative is gonna be the derivative of the thing over the thing itself. Okay, so the slope at 2 of natural log of x is 1/2. The slope at 5 is 1/5. You guys with me?
Mm-hmm.
Okay.
So u and v has become m and n.
Yeah, u and v has become m and n. So we still have notice that on your tattoo, I define M and N. They are functions, guys. I've also reminded you, this is not a derivative. It's not a derivative. Please, please, please don't treat it like a derivative. This is just that rewritten in a different form, okay? Still have to go through and take the derivative. Let's try another one. You guys ready? They're not so bad, are they?
No.
Oh, what? Oh, that's fully simplified. That's as pretty as it's gonna get. Do you like it? Yeah, they're pretty elegant, right? They're nice and clean, and that is if you try not to eat the whole steak at once. Don't eat the whole steak at once. All right, let's look at this one. Natural log of 6x plus 5 over 3x plus 6. So I want to demonstrate to you guys the difference between these two functions. First, what do you see?
You see 3x plus 6, not 5.
We see 3x plus,
6, not 5.
did I say that? Oh well, 5 is fine. I said 6 and wrote 5. F my brain. I'm sorry, you guys. Tavarius.
Does the logarithm apply to the denominator too? Or just-
That's a great question. What do you guys think? Did I assign the natural, is that tied to the natural log?
No.
Careful, 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 careful. So Devarius, your answer is no. It does not apply to the denominator as well. Here, the natural log is tied to the whole thing. Do you guys see that? This is why parentheses are so important. The placement of them tells you what's tied to what. So here, we have natural log of just 6x plus 5, right? On the denominator, we have 3x plus 5. And I keep thinking 6. All right. So this is a quotient, isn't it? It's a quotient that we can't split up, isn't it? Because it's not natural log of m over n. It's natural log of something over something else. You guys with me? So here's my u. Here's my v. My u prime, we're going to use the natural log process because my u is natural log of some junk. So the derivative of that is going to be 6 over 6x plus 5. And my v prime is just going to be 3. Is everyone okay with this?
Yeah.
So now what's my derivative? Use the quotient rule, u prime times v minus u times v prime all over v squared.
And that's just because there's only a natural log on the top.
Yeah. So you have to treat it like its own function. Brenda.
What if the log was in the bottom? Do you still do the same steps?
If there was a natural log of 6x plus 5 divided by the natural log of 3x plus 5, you could do this.
What if the ln was just under 3x plus 5 in the denominator?
Well, then your u would just be 6, or your u prime would just be 6, and your v
Okay.
prime would be 3 over 3x
Oh,
plus
okay.
5. You use the technique that's given to you based on the type of function you have, right? Just like we look at something and we say, that's a power, we use d out dn for powers. We look at this and we say, that's a natural log, we use the process for natural log to take the derivative. That's all we're doing here, okay? Let me show you why, if this were natural log of 6x plus 5 over natural log of 3x plus 5, that would work. I want you guys to take a look at, in your calculators, the natural log of 6 over the natural log of, say, 7. In your calculators, natural log of 6 divided by natural log of 7. You should get some number. You have it? Okay. Now I want you to test, after you've done that one, now I want you to test the natural log of 6 divided by 7. And then when you're done with that, try the natural log of 6 minus the natural log of 7 in your calculator. What do you see of all three of those? Two of them are the same?
Yeah, two of them.
Which two? The which ones?
Oh, the middle one and the bottom.
The middle one and the bottom one? Hmm.
I got
I kind of think all three should be the same.
I got the same.
Yeah, I think all three should be the same. I think you're right. All three should be the same. So do you guys see the pattern here? If you have natural log over natural log, you can just combine them. And if you combine them, then it looks like this, and you can separate them out and make it that. Okay? Natural logs are weird that way. You can do all kinds of manipulations to them, and they're all the same.
Then how did this view
I don't know. What did you plug in?
ln, or sorry, natural log 6 divided by natural log 7 got me 0.9207. Then when you just put it all together, and I got like maybe,
I'm getting the same thing.
That's weird, that you guys are getting a different number there. Gesundheit.
oh wow, you didn't believe in me?
You got it. All right. Let me see yours, just for giggles. Yours is also different. Oh, yours is, you told me that they were all the same. I thought they were different. Well, now I'm effing confused. Because it should be the same. It should be the same. All right, I'm gonna have to play with that. So hang tight on that. They should be the same. I'm like, I've never seen that before. I do not know what I'm looking at. So put a pin in that. No. We'll make a mark. Not excited by that. Oh God, okay, I think I see what I did, but I'm gonna make sure about that before I lose my mind and tell you guys about it, okay? So, yeah, just hang tight to that, and we'll tackle it together next time. Yeah, no, it's bad. I think I see exactly what I did. Now I'm all embarrassed. I need more coffee. Is my face red, you guys?
No.
Like flop sweat going down, a little trickle.
It's math.
It never makes sense.
No, it should make sense. It should. That's the thing, is when it doesn't make sense, my brain just goes, meh. I don't know what to do. I'm like, that doesn't make any sense. Mathematically, it should work. All right. Let's try one more, where we have to peel it all the way apart. Just all the way apart. You guys are gonna hate this. Natural log of, I think I already did one of these, right? Where it was an exponent and a quotient.
Mm-hmm.
I did one of those last time, didn't I? No? Okay, I'm gonna do it again. Brenda, you weren't here.
She was in Vegas partying.
Oh, is that what it was?
She didn't invite me, which I'm upset about, but
You're underage. You're a baby.
okay, I can still walk around and go to M&M stores.
Let's say this is to the So we look at this and we're like, oh, hell no, we're not gonna take a derivative of this right away. We're gonna choke on the steak. So look for the outermost function. It's something to a power, right?
Yep.
So we look for natural log of something to a power. Is there a shortcut for that?
M,
Yeah, what is it?
M to the power of P.
Yes, natural log of m to the power of p. So we can take, that's the same thing as saying natural log of m to the pth power. Notice the placement of parentheses here. P is still attached to m, no matter what you do to it, right? So we can take that p and we can drop it down in front. So we're gonna do that. So y equals 6 natural log of the stuff, one chunk at a time, guys. Okay, and now we're back to that quotient problem, right? So we would be using natural log of m over n becomes natural log of m minus natural log of n, and yes, I'm sure. Ah. So now my y, still not a derivative, 6 natural log of minus 6 natural log of 4x minus 10. Okay,
Where do you put it to the power of, like, 1/5, 1/5?
then that entire 1/5 would just drop down in front, and you would have 1/5 natural log of blah, 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 blah. So if this were all a square root, you would convert that to whatever root you have up here, and then drop it right down in front.
So it just drops and you don't do anything.
Yeah, there's no, here, this is not a D out DN problem, guys. This is not 6 drops down junk to the 5th, okay? This is an entirely different set of principles, which is why the logarithms have fully a quarter of your entire sheet on your tattoo, okay? They have their own set of rules. So now, are we in natural log of an easy u, something that we can simply take a derivative of? Yeah, so what is it? Y prime equals, minus 6 times 4 over 4 minus 10. Gesundheit. Why did the 6 go to both of those sets of terms?
That's in the bracket.
Because of the bracket. The 6 is tied to the 7x cubed term? Yeah. Is it tied to the 4x minus 10 term?
Yep.
Yeah. So it's gonna go to both of the terms when you go to the derivative. It's gonna go along for the ride on both of them. Alternatively, you can put a 6 and then bracket this entire thing to indicate that it would get distributed, but I like just distributing it right away so I don't forget. But that's personal preference. How do you guys feel about these?
So when we do natural log, whatever we are doing right now,
Uh-huh.
where would we apply this?
Any function. So for the same reason you guys are, I figured I would get this question at some point. People are like, where the hell do these functions even come from, right? And why do we care? The thing is, you guys, in business, you collect raw data, right?
Yeah.
You collect raw data. And that raw data can build a scatter plot. So let's say you have a profit that looks like a natural log function. So if you do all of the curve fits to see what the best curve fit is, and you get some natural log out of it, you can approximate your process, whatever it happens to be, if you're looking at revenue, if you're looking at average cost, if you're looking at profit, if you're looking at production, if you're looking at memorization, if you're looking at cleaning the air, scrubbing your waste treatment, whatever it happens to be, you can plot this using your raw data, okay? And that's where we get these functions from. Some of them end up being natural logs, that's all. So I'm just showing you the common the common types of curve fitting that we use in business, okay? Natural logs, exponents, and all kinds of rational functions go into making these. So it just depends on the application. Yeah,
Can you
various.
do another one with the power?
Oh, yeah, of course, absolutely. Did that answer your question?
Yeah.
Yes.
I did.
You did, does it make sense?
Yeah.
Awesome, okay.
So later on, we'll be having application problems, right? That will.
Maybe, if there's time.
Okay.
But by then, it's the same process, you guys. I don't know why you hate the application problems so much. They're just telling you to do the same thing that you do with the pure math. They're just telling you with words instead. Same stuff. How about this one? Natural log of, no, not a bracket. Hang tight, guys. Don't start writing until I've made the sausage. Because you know how this goes when I'm tired. Let's make that a square root. 3x squared minus 5 times x plus 6. So y equals that monster. Okay. Let's make it pretty. How do I make it pretty? Yeah, get rid of the radical. So this is gonna be natural log of 3x squared minus 5 times x plus 6 to the 1/2 power. Now what can I do with that 1/2?
Bring it down.
I'm gonna bring it down, you guys. I'm absolutely gonna bring it down. So that becomes a 1/2 natural log of 3x squared minus 5 times x plus 6. Is there a shortcut for that product in there? Natural log of m times n becomes what? Yeah. So now I'm just gonna rewrite that. Equals 1/2 natural log 3x squared minus 5 plus 1/2 natural log x plus 6. Is everyone cool with this? Do we have an easy derivative now? Do we have bite-sized chunks? Some easy natural log of some easy function? Yeah. So what's my derivative? Y prime equals
1/2 6 times 6x over 3x squared.
Yep, 3x squared minus 5 plus 1/2 1 divided by x plus 6. So I could simplify this just a little bit, right? I could make this 6x over 6x squared minus 10 plus 1 over 2x plus 12. Make it a little bit nicer looking, I would think.
So when we are applying this problem, I
Mhm.
mean, we do have the tattoo, but we have to get used to these, the
We have
log,
to get used to what, Marina?
the
I'm sorry.
tattoo. I mean, we would have to remember those.
You don't have to remember them. You get this tattoo on your
Cheat
test,
sheet. Okay,
in addition to your cheat sheet.
okay.
What?
That's awesome.
Yeah, but there's a trade-off. You guys have to come to class, come to class, come to class. From now on, we are in fast forward. Because we're about to hit reverse.
Yeah.
Just when you think you've mastered derivatives, I yank the rug out from underneath you and we start integration. So Every step we've done until now is building to that step. So don't miss class, guys.
And why do we do integration?
Why?
Yeah,
Well, the real payoff for business comes at the end of the semester. Do you trust me?
yeah, of course.
Okay. All right.
Of course. No doubt about that.
Have you guys ever seen supply and demand curves?
Yes.
Yes, I'm seeing it
Oh,
right now.
oh my
Yep.
dear.
Yeah.
Okay, that's the payoff, guys. We're gonna be integrating supply and demand curves. These are easier supply and demand curves. They don't have all the shifts, like you tweak this and it moves here, and you tweak this and it moves here. You guys have done those in economics, right? You've seen those in econ, and they're awful. But the basic supply and demand curve, how many of you guys have calculated consumer and producer surplus in your econ classes?
I have,
Okay, but you did it using triangles, didn't you?
yes.
Yeah, consumer and producer surplus aren't linear. They don't look like this. They're curves. So we're gonna be integrating under those curves to find those areas. Instead of approximating them as triangles, we're gonna be finding the actual numbers. That's the payoff in this class, guys. That's what we're working towards. Ruby? Okay.
So with derivatives, you kind of get an idea of how much one extra product will produce if we decide to produce.
Well, that's the derivative. That's what the derivative gives
Does.
you, is near future predictions. And you guys you'll use those as well. You'll use those as well. There's a reason why this is a fundamental class for you guys, and everyone has to take it. Because you start using these concepts later on in your degree. Maybe not in the real world, but in your degree, you'll certainly see them again. You will. Okay. Yeah, that's about as nasty as I want to show you guys. Let's go to the exponentials. Let's start on the next bit of this class. Oh, it's so good. Exponentials. And this is the third of the derivatives in your derivatives section. If y equals e to some power, the derivative equals u prime e to the u. So, did you guys notice how the natural log disappeared when you took its derivative? E does not disappear when you take its derivative. In fact, the entire original function is part of your derivative. So notice the pattern here. Whatever your exponent is, you take the derivative of that goes in front, and then you rewrite your entire original function. It never leaves, guys. It's still there. So far, so groovy.
Yes.
Why do we care? Here's what e to the x looks like. You guys remember natural log of x has a vertical asymptote. It crosses at x equals 1. This is natural log of x. Well, e to the x looks like this. It has a horizontal asymptote. It goes up like that, and it crosses at y equals 1. The cool thing about these is they're symmetric about the origin. So that if I draw a dotted line through this, pretend like my whiteboard is a sheet of paper and I fold along that dotted line, they would sit right on top of each other. Okay? They're also tied by the fact that natural log is log base e. Natural log is like saying log base e. Let me talk about why that matters. We can use this relationship to our advantage. So let's go back to base 10, because that's easy. What's 10 squared? What's 10 cubed? Okay, so if I said 10 to what power equals 1,000, you would be able to tell me, right? You would be able to say that this number is 3, because you know the relationship between 10 and 1,000. Well, if we use log base 10 to solve for that unknown exponent, we'll still get that same answer of 3. The base is 10, the base is 10. 10 to this power equals 1,000. 10 to this power equals 1,000. So if you use the log button in your calculator and you do log of 1,000, you're gonna get 3 out. But can we rewrite 1,000? can rewrite it, guys. That's the same as saying log base 10 of 10 cubed equals 3. 10 cubed is just 1,000, right? So I just substituted in 10 cubed, nothing changed. But tell me why that's important. Look at the pattern here. What are the bases? They're the same. What's this power?
Cube.
That's the answer. So if I use natural log of e to anything, I don't care what that anything is, that's like saying log base e of e to the x. Guess what that's gonna simplify to, guys? X. And that is on your tattoo. That relationship is about halfway down on the right-hand side. I need my tattoo out so that I may show you guys. That relationship is right here. Natural log of e to the x equals x. This is a simplification, it is not a derivative. Likewise, e to the natural log of x equals x. And the rule is, when the bases are the same, the exponent is the answer. You guys with me? Same pattern, it's the exact same thing. So if I give you a function that's really nasty and looks like this, y equals natural log of e to the 4x cubed minus 10x squared. Can you tell me what that simplifies to?
4x cubed minus 10x squared.
So that would be, we would find the derivative, right?
Well, yeah, I'll do it both ways, but I'm gonna show you why this is so much faster.
Okay.
Now what's the derivative of that, guys?
12x squared minus 20x.
Good. That's where we're gonna go. Now let me show you the long way to get that derivative. What's the natural log of anything? It becomes the derivative of the thing over the thing itself, right? So what's the thing in this case? It's e to the 4x cubed minus 10x squared. So y prime equals, I'm gonna rewrite the denominator, because I know that's gonna go there. Everyone cool with that? Okay, now what's the derivative of e to the anything? So now we're doing u prime in natural log of u. So now we use this process. So that's gonna be 12x squared minus 20x times the original function. What cancels? What are you left with? Okay, so which way do you like better? The red way or the shortcut?
Shortcut.
Yeah, damn straight you do, right? Yeah, you can get to it the long way, but it's gonna make you sad. Don't be sad. Be glad. Yeah, look for a shortcut. Is everyone cool with this? All right. This is a pretty picture. And if you guys want that over there, grab photos because I'm gonna erase it. La, 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 la. That's right, Maria's recording. She doesn't need photos. Goody! So now let's play a little bit with exponentials.
So are we doing some more problems?
Oh yeah, so many more.
Very.
Ooh, before I get started on that, let's go back to kindergarten, shall we? What did we do in kindergarten? A lot of us.
To 100.
We learned how to write. Because most of us knew how to read already, right? So then we learned how to write. You guys remember how to write in kindergarten? They taught you using this dotted paper. Do you guys remember this?
Mhm.
Oh yeah. So the big A gets 2, the little a gets 1. The big B gets 2, the little b gets 1.
It's one more.
Oh, you guys remember that? Now, raise your hand if you try to write so small that you can barely tell what's an exponent and what's not. Be honest. Stop that.
I think I write too big and then it looks like it's all.
Here's why. I'm going to be very careful about keeping numerators and denominators and fractions stable. Y equals 5/3 e to the 4x minus 12x squared to the 6th power. I have 4 layers here, guys. I have a denominator layer. I have a base layer here with the 5 and the e. I have an exponent of 4x minus 12x squared, and then I have an exponent of the exponent. I am being very, very careful, even on a whiteboard with no lines, to keep my parts on the right level, so I remember what goes where. Stop using the side-to-side notation for these. How many of you still put 5/3 in a slash instead of a, don't do it. You're gonna be a sad clown if you try. So get right into the top-down notation instead of the side-to-side notation. It's gonna make your life easier. Ruby? So now let's tackle this piece by piece. This is essentially a constant coefficient times e to some junk. What's my junk?
4x minus 12x squared.
I didn't hear the rest of it. To the
4x
6th.
minus-
Your u in this case is your entire exponent. It's
Oh,
everything
yes.
above your e. You guys with me? U is 4x minus 12x squared to the 6th power. What do we use to do this?
Can you use the chain rule or the
You're
power
gonna use
rule?
chain power d out, d in. So d out, 6, junk, to the 5th. That's d out. What's d in?
4 minus 24.
Okay. Tavares, did I give you your test?
No, ma'am.
Oh, it's here somewhere. I have it.
I'm not in a hurry to get it back.
I know, honey. It's okay. It's in here though. Here it is.
Oh, God.
I promised it to you this morning. There you go. And the solutions are on it.
Okay.
Okay. So that's u prime. So that's my u prime in the formula. So now what's my full derivative? Y prime equals what?
Y prime equals u prime,
All of that.
then you add the u again?
Yeah, the original function. 4 minus 24x. My original function had a constant coefficient that's going along for the ride. 4x minus 12x squared to the 6th. It takes more time to write it than it does to do it.
So what are we doing up there? I kind of lost that.
I'm gonna label everything.
Oh,
Here's
thank you.
u
Thank you
prime.
very much.
This is a constant coefficient. Goes along for the ride, right? They just travel. Coefficient, I can spell. And this is my e to the u. So essentially what I have here is u prime e to the u. So ask me questions while I hand this out. Talk to me, guys.
I have a question.
I have an answer. Hopefully it's right.
Can you do, a problem where the, can you have a
Yes, you absolutely can.
Can you do an example with the constant project?
Probably not gonna go that far in the real world, but if you wanna see one, I can do it with you in the office.
I had a hard time figuring out the action.
Yeah, we can work on that together. Hello, chickens. My quiet chickens. My quiet chickens. Yes. Now, we still have about 7 minutes, so let's do 1 or 2 more of these, okay, guys? Here we go. Okay. Alright. Oh, how about that one? So once again, I'm being very careful about what's on my base layer and what's on my exponent layer. What do you guys see? A what? A 4. What's next to the 4?
X.
An x. So is that a constant coefficient out front or a function out front? It's a function out front because it's got an x. So is this just a constant coefficient times e to the u? No, it's a function times a function, which is a what? That's right, it's a product, guys. Here's your u. Here's v.
Nice.
Don't worry, once you break it into bits, Christina, it's not so bad. I heard that. So now, Christina, I'm gonna pick on you, my dear. What's u prime?
4.
Good. And what's v prime? It's okay. Derivative of the exponent, I'll talk you through it.
Okay, 3x plus 5.
3x squared plus 5. Good, so that's u prime. Now what comes after that in the set? Yeah. Yeah. That's it. So see, that wasn't so bad. Break it into bits, guys. Now just plug and chug.
Why is this D?
Emily. It's not d out to the end.
Like, why doesn't it stop at there?
Here's u prime, e to the u. Because your v is some e to the u, this is the procedure we use.
So that's V.
Yeah. So now we have nested functions again, guys. Except now instead of products, quotients, and powers, we have products, quotients, powers, natural logs, and exponents. We have all that stuff mixed together, okay? It's all mixed together. So now we just plug and chug. Here's my blue. There we go. So y prime is gonna be u prime times v plus u times v prime. That looks like a negative, but it's not. And for consistency's sake, I'll just parenthesize that. So let me label my bits. Here's u prime. Here's v plus u. And here's v prime.
So essentially, this is the product rule in the end.
That's exactly what it is.
Yeah.
Yeah.
I'm behind the camera, so I was kind of wondering.
Yeah, that's exactly what it is. So it's a nested function. It's a product globally.
Yes.
Locally, we have e to the u on v. So we have to use the process for e to the u to take its derivative.
So
Right.
looking initially at the main problem, you see that when you divided it the way that you did u and v,
Mhm.
that should tell you you're doing the product rule towards the end.
That's right. If this had just been a 4 out front,
Yeah.
we could have gone forth and just done this, right?
Okay.
But because it's not a constant coefficient, it's an actual function, we have to treat it like a function, which means it's a function times a function, which makes it a product. Groovy, guys? Yes. Just stretching.
Thank you.
How do you feel?
Good.
What was the difference between knowing like whether it's that product times a product and the other one?
And just a straight derivative?
No,
What other
the
one?
one we did last time, the one we just did before that, right?
Yeah, without the x. The difference is that x. If this is just 4e to the x cubed plus 5x, this would be a constant coefficient and it would just go along for the ride. But
But it's a
because it
function of its
contains an
own.
x, it's
Okay.
got a function on its own. So you have to treat it like a function. So be careful for those little x's, guys. They're gonna, sneak in there and bite you.
So that formula at the end on the right-hand side really plays in it, this point.
Which part, this?
No, the one on your right, left-hand side. Right there.
What, I don't,
The y is equal to e raised to the power of
This?
u.
what about it?
There are two formulas, right, that we have to apply?
No,
Or we have to
no.
see which one applies.
Yeah, you have to see which one applies. This
Yeah.
is the formula for 11.1, this is the formula for 11.2. 11.1 went over logarithms. So if
Okay.
you have a natural log, you're gonna use this procedure.
Yes.
If you have an exponential, you're gonna use this procedure. I know it's about time, guys. So let me give you your homework.
Okay.
So on 11.1, I would like you guys to do 1 through 24 every other odd. Marginal cost. And demand not part C. If you try to do part C, you're gonna be sad. Okay? And then on exponentials, I would like you guys to do 1 through 36 every other odd. Future value. And sales decay. That's it.